name is Jason Hawkins. I'm an assistant professor at the University of Calgary, and I'll be the chair for this session on electric vehicles and sustainable freight. Um, so just a reminder to all of the speakers, you'll have about 20 minutes total. So if you can, 15 minutes for presentation, leaving 5 minutes for question and answer. So our first speaker is Yasser Kashwaa from McMaster University on integrated optimization of hydrogen production. Is that speaker here?
Yeah, I'm here. Thank you.
Great. So whenever you're ready, you can share your screen and start.
Okay.
In the meantime, I'm going to see if I can fix my lighting so I don't look so haloed.
Yeah. Is it okay now?
It's just coming up. Yep, whenever you're ready, if you can make it full screen and then feel free to start.
Okay. Yeah. So you can start now?
Yeah, go ahead.
Okay. Thank you very much. Hello, everyone. My name is Yasser Kashwaa, PhD candidate at Civil Engineering McMaster University. And today I'm presenting our work titled Integrated Optimization of Hydrogen Production and Distribution for Multi-Depot Fuel Cell Electric Bus Network. This research focuses on a practical planning and configuration of introducing hydrogen fuel cell buses to transit network. First of all, I would like to acknowledge that McMaster University is located on the traditional territories of Mississauga and Haudenosaunee nations, with the lands protected by the Dish with One Spoon Wampum Agreement. I would also like to acknowledge that this work is supported by INSERC and NRCan, and I'm also grateful to Dr. Foda and Dr. Mohamed for the guidance throughout this research.
Yeah, sir, if
As
you
you
wouldn't
see,
mind, could
yeah,
you share your video just so we can see you when you're
uh,
presenting?
okay. Okay. Sorry.
Perfect. Okay,
Yeah.
continue.
Okay. Is my screen is appear now?
You'll just have to go into full screen mode again.
Okay. Yeah. Now it's appeared?
Yep.
Yeah,
Yeah,
okay.
go ahead.
Okay, as we see in the figures that the transportation account 22% of greenhouse gas emission in North America, with public transit account 6% of transportation greenhouse gas emissions. So rapid actions are required. And one promising solution is hydrogen fuel cell buses. Why hydrogen? Because hydrogen is a clean energy source and it can be transported over a long distance and it can be stored for a long term. So hydrogen fuel cell buses are often viewed as a promising option for decarbonizing transit service. Now, in terms of powertrain comparison, battery electric buses require distributed charging depot and sometimes en route, and it can be constrained by grid capacity and longer charging time. On the other hand, hydrogen fuel cell buses can use centralized production and flexible refueling with faster refueling and suitable for longer routes, which can be suitable for high demand and long distance routes. But transitioning to hydrogen in transit systems faces several challenges, which can be classified as economic challenges and energy integration challenges and operational challenges, mainly on chain coordination and bus scheduling. That brings us to a multi-depot hydrogen system, a rail transit network with multi-depot. We face several planning questions, which are where should hydrogen be produced, centralized or decentralized? Centralized means that uh, produce hydrogen on site in one depot and transport the hydrogen to other depot, or decentralized to make each depot has its own on-site hydrogen production, or another option to import hydrogen from external market. If we will go with on-site production, how large electrolyzer and storage be? Another question, should all buses refuel at each its assigned depot or allow crossing depot refueling? How much hydrogen can be shipped between depot each day if we suggest centralized production? To answer these questions, we uh, like we addressed all these questions in our journal paper, which titled "An Optimization Framework of Hydrogen Fuel Cell Buses in Multi-Depot Urban Transit Network." In this paper, we developed a mixed integer linear programming framework that jointly optimized depot production, storage, filling structure, and inter-depot transport, with aiming to minimize total annual cost and meeting daily service demand. Uh, the framework is designed to support integration of hydrogen fuel cell buses with multi-depot transit system. And this paper also is applied to a case study of Halifax with 5 different configurations are evaluated and compared. One key configuration is centralized hydrogen production, where one depot acts as a production hub and the other with electrolyzer and storage, and the other depot primarily serves as a demand node that refuel buses. Then we optimize when and how much hydrogen to be transported between depot so that the refueling demand is met reliably without shortage while minimizing the total system cost. This slide shows the overall flow of our proposed optimization model. We began with the input layer, which contained depot locations, distance between depot, and daily PV power generation, and electricity time of use, and bus scheduling, and all other uh, system data. The model then processes input through an optimization framework aiming to minimize total annual cost, including capital cost and operational cost. Finally, the model generates the output which identify which depot serves as hydrogen production and which serves as a refueling hub. It also determines the optimal infrastructure sizing, including electrolyzer and storage and dispense, and the number of dispensers required, as well as operational decisions such as daily power demand, hydrogen production levels, and the inter-depot hydrogen transfer, and the bus refueling strategies. Uh, the we apply the as we see that the optimization model aim to minimize the total annual cost, including capital cost. The capital cost represents the total investment cost, including infrastructure cost and hydrogen fuel cell bus cost, while operational cost included four main cost categories, which are electricity, electricity cost, the social cost of greenhouse gas emission, and the electrolyzer operational cost, and inter-depot transportation cost. We apply our model to a case study of Brampton. The data is extracted from GTFS with around 5,000 daily trips served by 570 operating bus. And also in Brampton, we have 3 depot, Sandload, Clark, and Cadita. And in this study, we consider the electrification of 10% of bus fleet using hydrogen fuel cell buses, allowing us to evaluate the system performance under partial transition scenarios. Now we will head to the results. We see that the total annual cost is around 12 million, 12.5 million dollars, with annual cost about 8.4 million dollars, and annual operational cost is around 4 million. We see that the bus cost is the largest capex driver. Here in the capex distribution, if we exclude the bus cost, which is the largest one, we will see that the electrolyzer accounts around 40.7 from capex from the annual capex cost when we exclude the bus cost. And then the transformer also is the second highest with 30.7%. On the operational slide, we can see that the grid electricity dominate the operational cost with around 81.7 of total operational cost. So overall cost is heavily influenced by capex and by vehicle capex, vehicle cost, and the grid electricity dependence. Here are the optimal configuration of our system. The model chooses sand load as a production depot. Sand load has a 26 assigned bus. It produces daily around 1700 kilogram hydrogen, and it's imported 630 kilogram to the first depot, which is called Clark, and the 280 kilogram of hydrogen to depot Candida. Also, from cost perspective, we can see that the model is highly dependent on electricity, on-site hydrogen production, with electrolyzer around 4 megawatt capacity. And also we can see that from cost perspective, the total rely on electrical grid is more cost effective than using other power sources like on-site solar generation. And this is due to the high capital cost related to the PV panels, and also the large space required, which will be restricted in depot. Also, the model determines the optimal tank size for each buses, which can see ranges from 35 kilogram to 45 kilogram for bus tank size. This figure also show the daily energy flow and highlights the key operational dynamics of the system. The green light shows the tank hydrogen tank level in the tank storage, while the dashed orange line shows the electrolyzer production rate. The red bars shows the importing events, while the blue bars shows the refueling events for buses. We can see that the production peaks around the mid of the day in order to build the high storage to supply other depot, and also store the hydrogen to refuel the assigned buses to this depot at overnight. Also, for the importing depot, there is no local hydrogen production as shown as a flat electrolyzer line. Instead, the hydrogen is delivered through import levels for both of depots. For first depot is around 13 p.m. time, and overnight at 22 p.m. for the second depot, in order to fill the storage and to refuel the buses overnight when the bus finished its services. To conclude, centralized hydrogen production can be economically in multi-depot transit system. In our Brampton case study, Sandalwood Parkway is selected as the optimal production hub, producing around 1700 kilogram hydrogen using a 4 megawatt grid electrolyzer. The proposed model enable efficient centralized coordination of hydrogen supply and refueling demand across the network, and it demonstrated a technically effective busway for municipal transit decarbonization. Uh, from a planning perspective, first, centralized hydrogen production can be cost effective, but it remains strongly dependent on grid infrastructure. Second, PV powered on-site production requires significantly high capital cost and large land area, which can be limited in urban depots. Third, the primary barrier remains in the high capital cost of the hydrogen fuel cell bus itself. Overall, optimization frameworks can support deployment decision, station siting, sizing, power and energy management, bus configuration in terms of bus optimal tank size and bus refueling patterns, with aiming to minimize the total annual cost of electrification of transit network. And that's conclude my presentation today. Thank you for your time, and I'm happy to take any questions.
Thanks, Yasser. Any questions for Yasser? Yeah, so Andrew Moth has a question. Does your model determine a hydrogen price? And if so, what is it in dollars per kilogram?
Yeah, in our model, is the in the model in the basic model, if we import hydrogen from market, which is not in this case study, the cost of hydrogen around $9 per kilogram. But here, the model in this study, we didn't like we didn't compute the how much kilogram will be cost for each kilometer, but we can calculate it.
Okay. Yeah, so Vince Bernardin asks, why do you assume central production of hydrogen rather than distributed?
Yeah, I think for centralized production, it will save money instead of building the same infrastructure for on-site hydrogen production in each depot. So we build also in one depot, and we will manage the hydrogen transportation to other depot instead of making on-site production in every depot, because every on-site production require also safety considerations that must be included, and it will be included in our future work.
Yeah, great. Well, I have a question.
Okay.
So you're optimizing hydrogen facilities here. I'm just curious how does the objective function and the constraints in hydrogen uh, refueling, does it differ in any way from battery electric?
Yeah, from uh, we have for two best ways. The hydrogen fuel cell buses still have high costs in terms of buses if we compare it with battery electric bus. Okay,
Hmm.
but hydrogen fuel cell buses have uh, advantage over battery electric buses, as it can be considered as a diesel bus. So it has a fast refueling. It need only a fuel which is considered as hydrogen. So
Hmm.
the optimization model here is how to meet the daily demand of each transit network for hydrogen, if we want to electrify all the transit network with hydrogen buses. But this doesn't mean that battery electric buses is not a good option. Battery electric buses have its advantage, especially for not long, small routes. So from my perspective, the best way is to use the both advantage of both technologies, and design models to incorporate the both technologies in our transit networks.
Great. Well, if there's any other questions for Yasser, feel free to ask them in the chat box and he can respond there. But otherwise, we'll move on to our next speaker. And I should say, I apologize in advance if I mispronounce anyone's names. Miki Tsuchiya from Carnegie Mellon University on slow steaming for trucks. Automation changes the trade-off between productivity and environmental performance for electric trucks.
Uh, Thank you for your introduction. Can you see the screen?
Yep, whenever you're ready, go
Yeah,
ahead.
sounds good. So somehow the program says I'm
Yeah,
Carnegie Mellon,
yeah,
but I'm from
yeah. I
University
was
of
gonna say, I
Michigan. My
think,
name is Miki Tsuchiya. Yeah, thank you so much for having me here. So today I would like to talk about long haul trucking in the United States. So the long haul trucking vehicles are running like 150 miles to over 3,000-mile routes across the continent, which is quite long for a driver to complete. And the vehicle itself is very heavy and one of the largest ones that we can see on the highways. And these vehicles are carrying 10 to 20 tons of payload. So it is a very heavy vehicle and running quite long distances. So these vehicles are facing two emerging trends, which are electrification and automation. I would like to talk about these trends in this study. First trend is electrification. So this is in need of the sector's decarbonization, but long haul trucking accounts for only 9% of medium heavy duty vehicles in fleet size. However, it accounts for around half of medium heavy duty vehicles GHG emissions. This translates into 10% of transportation emission in the US and 3% of total country's GHG emission. So we can say it is critical to address emission of the sector. Past study has been discussed and proven that electrification can reduce GHG and air pollutant emissions. However, it is generally considered very challenging to electrify these huge vehicles or trucks because it is very expensive and physically heavy. Batteries are required to compete this 800-mile range of diesel trucks. And then also charging infrastructures are limited on the highways for heavy-duty vehicle to access in the US. However, market is rapidly expanding in this area. For example, Tesla Semi, these are covering 500-mile range with a single charge. So the market is leaning towards electrification despite these challenges. So second trend is automation. So when we say automation, we refer to driverless full automation. So the automated truck will remove human labor needs, which will sharply reduce the cost because around 40% of trucking cost is currently human labor. And then also we can increase trucking productivity because machines do not have to be like rest as the human are mandated to rest for like 10 hours after 14 hours of shift. So the operation cost and productivity will be improved. However, there might be a trade-off with the productivity because the automation may remove opportunity of overnight charging, like charging while the drivers are sleeping overnight. So in this study, we would like to combine slow trucking, like just driving slow concept, to see how we can maximize the benefit of automation and electrification of trucking. So slow trucking or slowing down is actually happening in the US. So this is a Wall Street Journal article 2 months ago. These reports that because of the current fuel price rises, truck drivers are actually driving slower by 4% in April compared to January this year. And then so they're driving around 62 to 65 mph, which I feel like it's lower than what I think truck drivers are driving. So yeah, it's happening. And slow steaming was term originally came from ocean shipping industry. So the ocean shipping industry applied the operation of slowing vessels down to keep fuel emissions reduced. So they have been successfully keeping the emissions constant over the decades. Even the trade is expanding like plus 40%. So the bigger trucks are also speed dependent as vessels. So the combining this concept with automation and electrification might increase fuel efficiency or the EV range and reduce the emissions or environmental impacts. So when I present about this study to colleagues or like fellow researchers, people worry about the risk of crashes. Like if you go slower than other vehicles, like can we go increase the risk of crashes? So of course, some studies are digging into it and showing it is likely increase the risk of crashes if you go too fast compared to other vehicles. However, it is inconclusive if in case we go too slow compared to other vehicles. And we are thinking it may end up being safe to operate these trucks slower because we assume there are no drivers on board. So we leave this discussion as limitation and going on analysis based on the fuel economy and productivity. Yeah. So in the study, we address these three research questions. One is, can slow trucking increase EV driving range? Second is, can automation compensate the extra shipping time by going slower? Third is, how much environment and health damages can we reduce? So in our research, we assumed to automate only on highway routes. So the truck coming from urban roads enter into truck port, trailers are swapped to automatic one from human driver, and then complete the highway segment without human drivers. And then at the exit of highway, we swap back the trailers, and then human drivers can complete the rest. Because the urban segment is a little bit complicated, and then for the automated machines, it might be less feasible for them to complete in the near-term future. So also we compared driving profile of 60 mph as a regular highway speed, and testing the 45 mph as a slow speed because this is the light above the minimum limit for trucks for many parts of the US. So we used the real-world tracking routes and the ton-mile shipping data obtained from commodity flow study. We identified 16,000 origin-destination pairs. And then using the Google Map API and open source routing machine API, we get the exact GeoJSON data for the tracking routes. And then we apply the DriveCat driving profile to these routes. And then for each route, we developed system modeling to calculate energy consumption, number of charge breaks and location, and time to complete the travel. We also using the LCA method to calculate the GHG and air pollutant emissions in monetary value, considering upstream, tailpipe, and a lifetime emission stages. Okay, then I will show you some of our results. So yeah, we modeled out with a 500 kilowatt hour battery, how many charge breaks truck needs to take and for each route with various lengths. So the result shows that slowing down from 60 mph to 45 mph will increase the EV range by 25%, which sounds like a very significant improve. And for charger demand, slowing trucking will reduce the required charge stop per route from 3 to 2 at median, like we can see in the map. And because we know the location of each charge stops, we plotted the intensity of charge demand and the annual power usage of each location. So this is slightly hard to see, but the top two maps are showing the 60 mph speed scenario, and the bottom two maps are showing 45 mph scenarios. And yeah, we can see the slowing down can reduce the overall charging demand. We can see the bottom two maps are slightly lighter color compared to the top two maps. Yeah, so, all right. Yeah, the overall the color is getting lightened, but we can see the slightly shifting the location at the highest demand. So maybe like some of the parts are darker, but like the other parts are getting darker when going slower, which is we found interesting. Right. So let's move on to the duration or productivity. So we compared three scenarios. One is human drivers with diesel trucks, and the other is automated electric truck cruising at 60 mph and 45 mph speed. So the human scenario includes the rest period, like overnight 10-hour shift resting after 14 hours shift. And electric trucks include charge breaks as needed. So the result shows that automated trucking is mostly faster than human drivers for routes longer than 650 miles, which is shaded in this green or blue boxes. This accounts for 60% of annual ton-mile shipped, so more than half. So this is true whatever the speeds are. So like even going slower, it is still faster than human-operated diesel trucks, including the rest. So we can say the trucks can be automated, electrified, and slowed down without losing any productivity for those routes. So for those routes, we can discuss about the trade-off of truckers giving up some of the productivity gain and get fuel economy benefit or environmental benefit that we can discuss in the next slide. Yeah. So the GHG and the criteria air pollutant emissions are here. We compared between the same three scenarios that I showed in the previous slide. And we found that electric trucks emit lower GHG than diesels, and slowing truck can further reduce the emissions. And for the total externalities, the reduction can sum up to 800 million at 60 mph compared to diesel trucks, or 2.4 billion at 45 mph. So like more than 1.5 billion of gain by going slower. So in conclusion, slowing trucks increases the EV driving range by a fourth, and reduce the en route charging demand by a third. So for longer routes that ship more than half of the annual ton mile, automated trucks can eliminate the human rest period and get more productive. So, and third, electric trucks, slowing down can enhance the environmental health and health benefit of electrification compared to diesel trucks. So yeah, this is the last slide. But yeah, in terms of policy, so our study has shown that automation only on your highway track can improve the productivity and reduce the operator costs for longer routes. So maybe the trucking operators may give up some of these productivity gains by going slower to reduce the environmental and health externalities to accelerate, and also to accelerate the transition to electric trucking. So yeah, I have to note finally, like currently the charging infrastructures are not are prohibited in interstates in the US, because like it is originally restricted to protect the commercial activity on the town or city that bypass the highway. However, the trucks are not, like automated trucks are not gonna eat sandwiches or anything on the way. So that logics are not applicable. So maybe the policy can be updated for the automated trucks to charge en route. Otherwise, they have to get out of the highway to charge and then come back to the highway, which might be technically difficult or socially not acceptable. So the policy need to address to make this system come to the reality. So yeah, that would be all, and thank you so much for listening.
Thanks. So some really interesting questions in the chat. The first question from Alexander Granado is, they say, my car shows a lower gallon to mile ratio at higher speeds. Is the opposite true for electric trucks? So I guess saying, the vehicle seems to be more efficient at higher speeds. Is that different for electric trucks?
So the diesel trucks have the specific sweet spot for the operation. So like maybe they have to drive in the maybe like for 60, like 50 to 70. I don't have that in my mind, but like I saw the the chart. However, the electric trucks have like the flat efficiency rate, and then like if you go very slow, of course there are like carb that lose the efficiency, but the system is different depending on what the powertrain it is.
Yeah, I think that's generally true. Yeah, so then Kara Kockelman asks about speed governors. I guess heavy duty fleet operators say that they have speed governors that don't let the vehicle go over 75 or 70 miles per hour, but you can see heavy duty trucks going 80 miles per hour on the highway. Um, do you have any uh, insights on that question?
What type of top speed governors do other nations have? Is it a question too? Sorry.
It's not really a question.
Okay.
But yeah, I was asking everybody, what are the governors in your nations? Maybe, that of other places in the world. There's a lot of expertise here in this room. So feel free
Yeah.
to type in some responses, anyone from anywhere. What are trucks governed at in your countries or like other places that you've studied?
Mhm. Yeah,
Canada? Jason, anything in Canada?
not that I'm aware of, but I was going to say when I still have a project in the US for FEMSA that's on commercial vehicle safety. So I was interested. I hadn't heard about this movement towards uh, slow steaming for trucks. That's
Yeah.
interesting.
Yeah.
And I guess sort of related to that point, Andrew Moffat has a question of by traveling slower, isn't there a risk that the environmental and economic benefits for an individual truck are offset by needing higher capacity on the route, so potentially requiring more trucks to satisfy the same demand?
Yeah, that's a good question. Thank you. So that is why we wanted to test how the automation can like chime into that issue. Like just going slower, maybe like if you are just going slower with the diesel truck with the human drivers, maybe we will need more capacity. But we are testing how the automated trucks can win or like go faster in the end compared to the human-driven ones. So they do not have to rest. They do not have to wait for like a few hours after the shift or 10 hours overnight. So like overall, they are like improving the capacity issues, even though the trucks are driven slower, if that makes sense.
Great. It doesn't look like we have any other questions, but there's some discussion, I guess, in response to Kara's discussion in the chat box. So if other questions come up for Miki, feel free to put them in the chat box. So our next speaker will be Aditya Mehta, who I believe is not here, but provided a recording for us.
Hello everyone, and thank you to the session chairs. My name is Aditya Mehta, and today I'll be presenting our work evaluating zero-emission last-mile delivery strategies in urban Seattle, comparing electric cargo bikes and battery EV vehicles through a vehicle routing lens. Urban freight is a growing problem for cities. E-commerce growth keeps pushing more smaller delivery trips into dense neighborhoods. Those delivery vehicles compete for scarce curb space, which worsens congestion in freight, as it is a disproportionate contributor to local air pollution and greenhouse gas emissions. In response, cities are moving towards low emission zones, which just restricts high emitting vehicles towards stricter zero emission zones for freight. which only admits zero tailpipe emission vehicles and pairs that restricts with freight specific rules, delivery windows, vehicle classes, and integration with micro hubs. So the research question is, how should e-cargo bikes and battery EVs be deployed within a prospective zero emission zone for freight in central Seattle? And under what conditions does each mode or hybrid of both minimize cost and emissions? Our approach has 4 steps. First, we frame last mile delivery as a heterogeneous vehicle routing problem covering both bikes and battery EVs. Second, we formulate that as a mixed integer linear program with capacity and battery EV range constraints. Third, we parameterize cost and emissions from empirical literature and Seattle relevant conditions. And fourth, we compare bike only, battery EV only, and hybrid fleet strategies across stylized zero emission zone for freight scenarios. Before the model, it's worth grounding in what the literature tells us about these two modes. E-cargo bikes typically carry 1.5 to 2 cubic meters, which is about 10 to 15 parcels a trip, with a daily range of 20 to 40 kilometers. They shine in dense urban cores, narrow streets, bike lanes, minimal curb footprint. Battery EVs carry far more, around 8 to 12 cubic meters, which is around 2 to 400 parcels per route, with a much longer range of 160 to 300 kilometers, making them suited to standard road networks and longer routes. On cost, bikes have lower capital cost but higher labor cost per parcel. Battery EVs have higher capital cost but lower energy and maintenance cost per kilometer. Both are zero tailpipe emission, but bikes further ease congestion and noise on narrow streets, and battery EVs still compete for curb space. To formalize this, we build a heterogeneous vehicle routing model. Bikes treated as low capacity vehicles that can make multiple trips from micro depot. Battery EVs are medium capacity and range constrained and can also act as feeders for bulk loads to delivery to micro depots and zone periphery. Both modes serve customers within zero emission zone for freight under shared constraints. The objective is to minimize total generalized routing cost, time plus energy across all vehicles and arcs. Key constraints are every customer is visited exactly once, flow is conserved at each node, and routes starting and ending at the depot. Vehicle load can never exceed the capacity, and battery EVs, specifically energy consumed between nodes, can't exceed remaining battery charge, with recharging modeled at designated nodes. Small instances we solve exactly with MILP solver. Larger, more realistic instances you use a math heuristic combining MILP relaxation with neighborhood search. For Seattle scenarios, we ground our parameters in the literature. E-cargo bikes, energy use of 0.01 to 0.02 kilowatt per hour per kilometer, and daily range of around 20 to 40 kilometers, which comes up to with the capital cost of $5,000 to $10,000 per unit, with labor per parcel as dominant cost driver, given manual handling in shorter routes. On the other hand, for battery EV vehicles, energy use of 0.2 to 0.3 kilowatt per hour per kilometer, with a daily range of 160 to 300 kilometers per day, higher per charge, higher capital cost than diesel vans, but offset by a lower fuel and maintenance charge over the vehicle's life. Both modes are zero tailpipe. What differentiates their environmental profile is upstream grid emissions and non-exhaust externalities like congestion, noise, and curb use. Why Seattle? The city combines high e-commerce activity with an ambitious climate target of around 30% of goods delivered by zero emission by 2030 under transportation electrification blueprint. It's also already run a real pilot in the uptown region called as the neighborhood delivery hub, testing a micro hub with zero emission modes. At the same time, Seattle's constrained street network and limited curbside space creates a real operational pressure, and its existing cycling network is a natural fit for e-cargo bike operations. We use this context to define 3 stylized fleet scenarios. One is bike only, the second one is battery EV only, and the third one is hybrid across short and medium route lengths. These are the illustrative results. Holding demand constant across all 3 scenarios. Scenario 1, bikes only on shorter dense roads. 120 kilometers of total distance comes up to $1,300 a day. $3.25 per delivery, and 0.15 kg of CO2 emission per delivery. For scenario 2, battery EVs only on medium routes, more distance and higher cost per delivery, coming up to $3.63 per delivery, reflecting that bikes forced into longer hauls or battery EVs on short trips are both inefficient in their own way. Here, battery EVs are just handling a longer route than bikes could efficiently cover. For scenario 3, the hybrid battery EVs feeding the micro hub with bikes completing the final leg comes out for the best overall. Lowest cost per delivery at $3.12 and lowest emissions at 0.14 kg of CO2 emission per delivery. The takeaway, bikes win on short and dense routes, battery EVs win on longer routes, and hybrid captures the best of both. None of this could have happened without policy support. 4 levels matter the most. Zone design, which includes boundaries, vehicle eligibility, fees, and freight specific exemptions. The second one is infrastructure, charging for battery EVs and safe cycling networks, plus siting for the micro hubs. And third is incentives, purchase subsidies, tax credits, and curbside access priority. And the fourth one is data and governance, data sharing agreements between public and private partnership and companies that support integrated planning. In our framework, these levers show up directly as model parameters, which let us evaluate policy scenarios before the event. Coming to the conclusion, our analysis supports a hybrid strategy for Seattle. E-cargo bikes should dominate short and dense routes within zero-emission zone for freight, especially near well-placed micro-hubs. Battery EVs should provide high-capacity service on longer routes and act as feeders to the micro-hubs. And policy and infrastructure zone rules, charging, cycling networks, incentives remain the critical enablers that make the deployment feasible. Future work on this topic includes embedding Seattle-specific demand and network data, incorporating stochastic and dynamic routing, and modeling how carriers and shippers actually respond to zero-emission zone policy. Thank you so much for giving me this opportunity to present in front of you.
Great. So my understanding is the authors for this paper weren't available, but I posted Aditya's email in the chat box. So if you have questions for him, feel free to send those questions there. But otherwise, I think we're making very good time. So we have plenty of questions for the speakers who are here today. So moving on, our next speaker will be Lynn Su from University of Texas at Austin, presenting on dynamic smart charging through integrated agent-based and optimization modeling. So I know Lynn is here.
Yeah, I'm here. Thanks for the
Okay.
introduction, Jason.
Perfect.
Let me share my screen.
Yep.
Is my screen visible?
Yep. Whenever you're ready.
Okay. Morning, everyone. Thank you for joining this presentation. My name is Lin Su from the University of Texas at Austin. So today I will be presenting my work on the dynamic smart charging of a mixed EV groups, including fleet and personal EVs, through an integrated agent-based and optimization modeling. And this work was conducted under the guidance of Dr. Carl Kockelman. The smart charging, including the unidirectional charging V1G and the bidirectional charging V2G, provides an opportunity to better coordinate EV charging with grid conditions. Through shifting charging across time, it can help smooth grid loads, support renewable energy use, and improve the overall grid reliability. The fleet EVs are particularly well suited for smart charging and V2G because they are centrally managed and generally have predictable operating schedules and controllable charging patterns. So with V2G, the fleet operator can also potentially gain additional revenue by providing energy back to the grid when those vehicles are idling. And the household EVs also represent another important resource. Although they are individually operated, their large population and relatively long idle periods also provide potential contribution. However, most prior work studies smart charging focus on a single EV group, and they always assume the V2G is available throughout the day, and their approaches struggle to capture the two-way feedback between optimized charging schedules and the evolving system conditions. So in this work, these challenges are overcome by developing a V2G framework combining both fleet and personal EVs. And the V2G will only be triggered under the favorable conditions. And this designed optimization framework is coded and implemented in an agent-based model, thus enabling the dynamic interactions between charging decisions, travel demand, and system performance. The agent-based model can simulate the vehicle operation and moments, charging behavior, network congestion, and continuously track EV battery conditions. And the simulated system status will be delivered into the optimization model to get the most cost-effective charging and discharging schedules. And this, the dynamic two-way feedback allows the optimized charging decisions to inform the fleet operation with while the agent-based model can capture the resulting travel response. The objective of this designed V2G model is to minimize the system-level energy transaction costs over a simulation day. And the decision variables include the energy bought and sold by the fleet, and also the energy bought by the households. The cost components listed here include the electricity purchase cost and the monetized environmental damages associated with energy generation. When the vehicles participate into the V2G, they can earn discharging revenue, but at the cost of the battery degradation. And to maintain a reliable fleet operation across multiple days, a large penalty will be added for the deviation from the fleet's targeted state of charge by the end of the day. The optimization is subject to several operational and grade-related constraints. From the fleet operation perspective, the energy balance must be maintained throughout the day, and then to protect the battery health and avoid excessive discharging. The average fleet SOC is constrained within the defined bounds. So in this study, we assume the average fleet SOC is constrained between 10% and 100%. And in addition, the average fleet SOC over the next several hours must remain above minimum threshold to ensure the reliable fleet service. And so here we assume the average fleet SOC over the next 4 hours need to maintain above 40%. And the supplied EV charging station configuration, including the number of the direct current fast chargers or the level 2 chargers and the charger power, together constrain the energy can be bought or sold by the fleet or the household. So only if there is great need, that is when the great demand exceeds certain level of the supply, then the V2G will be triggered to allow the vehicle discharge their energy back to support the grid. The case study area is within the Austin 6-county region in the Texas state. And the EV fleet is assumed to be composed of shared autonomous electric vehicles. and they are providing ride-hailing services at a cost of $2 pickup fee plus $0.9 per mile and $0.25 per minute. And for those travelers who are willing to share rides, they can enjoy a 40% discount. Based on the prior study, we assume a 40% household EV participation rate for the V2G. So total 4 scenarios are evaluated. The level of grid interaction is gradually increased. From the very beginning, the last minute charging does not provide any grid support and reflects the conventional scenarios. So the charging behavior is totally driven by the battery status. For example, once the SOC is below 10%, the vehicle will be assigned to get recharged. And then move to the unidirectional smart charging V1G. The fleet charging schedules will follow the optimized charging decisions, thus reshaping the energy demand over time. And then move to the bidirectional charging, but only for the fleets. It allows fleet vehicles to discharge their energy back to the grid during the grid stress hours. And then finally, the combined V2G expands the fleet V2G by incorporating both fleet and personal EVs. Thus more vehicle groups can support the grid. And then the electricity market and the grid data used in this study are obtained from ERCOT, which serves 90% of the Texas electricity demand. And also a reserve margin threshold of 21% is used to indicate the grid stress status. So to capture different electricity market conditions, 4 representative wholesale price patterns are classified based on the within-day price variability. And also the time of use price signals is also considered based on the price from the city of Austin. Here are the fleet service performance under 4 charging strategies. The 3 smart charging scenarios present similar level of service performance. Across all scenarios, the median passenger wait time maintained below 5 minutes, and on average, each EV serves roughly 31 passenger trips per day. And the daily vehicle miles traveled increases from 255 miles per SAEV per day under the last minute charging strategy to roughly 285 miles per SAEV and the smart charging scenarios, along with the empty VMT share increased by 5%, indicating the additional repositioning associated with charging and discharging decisions. The smart charging also reshapes the fleet charging patterns. So from the left figure, we can see under the V1G, fleet charging mainly concentrates during the midday and late night hours, while morning charging during 6 to 8 a.m. Is nearly eliminated. And the fleet V2G largely preserves the observed V1G charging pattern, while allowing the fleet EVs provide targeted discharging during the grid stress hours, typically during night from 7 to 11 p.m. And the combined V2G introduced household EV discharge covers broader afternoon and evening grid stress periods, although at relatively small magnitude. So from those results, we can see with a greater intraday price variation, such as under the spike and time of use price signals. The incentives are kind of stronger load shifting and V2G participation for the energy arbitrage. And also one key advantage of smart charging is their environmental benefits. The V1G can reduce the net carbon dioxide emissions from 65 kilogram per vehicle per day to below 55 kilogram, while also lowering the carbon intensity per mile by up to 28%. And the fleet V2G presents the best environmental benefits. It achieves the lowest per vehicle emissions as below 50 kilogram carbon dioxide, and also per mile basis output is below 0.18 kilogram per VMT. The combined V2G has slightly higher fleet level emissions, but it still performs better than the V1G scenario, especially with additional household EV participation. It can save aggregated carbon dioxide emissions by up to over 4,000 kilogram carbon dioxide per day. So overall, the designed three smart charging scenarios represent a gradual path towards the increasing level of vehicle-grade interaction. The V1G is the most practical near-term deployment and achieves the lowest implementation cost, while the fleet V2G and the combined V2G is a long-term goal, as the V2G capable charger requires expensive upfront costs, which may discourage fleet and household EV owners from participating into it. But those costs are expected to decline as vehicle electrification and charging technology mature. So to conclude, our results show that the fleet V2G can preserve most of the operational benefits of V1G while providing targeted support to the grid. And by further incorporating the household EVs, the combined V2G provides greater flexibility for grid support. And we also find that the greater within the electricity price variation can create stronger incentives for both load shifting and V2G participation. Looking ahead, more accurate travel demand forecasting and effective coordination across the transportation and power sector remain important challenges for large-scale V2G deployment. Thank you all for your time and attention. This is the end of my presentation, and I will be happy to take any question.
Great. Yeah, so a few questions for you, Lynn. I see Kara responded a little bit to this first question, but maybe you can provide some response too. Are there plans to model this with school bus fleets? They have very large batteries, so that was from Jane Gould.
Like from my understanding, I feel like with bigger batteries that will be more suitable for the V2G, because currently we are using the SAEV fleet, which has a battery capacity at 90 kilowatt hour. So it will like have relatively limited battery capacity compared with the school bus. So I think with like larger battery, it might have much better performance like compared with the current EV fleet.
Yeah, so I think actually our next speaker had a question for you. Janak Parmar was asking, what compensation level would be needed to sustain these various participation rates? Would you consider replacing? Sorry, I just lost it, and maybe you can also maybe read it. Would you consider replacing the fixed fraction with a stated preference or choice model of participation so that opt-in response endogenously to price spread degradation concern and grid stress frequency?
So currently, in our model, we select the V2G reward based on the incentive like shown in the provided by the city of Austin, but it was like time dependent rewards and also it's on the fixed rates. But like the V2G participation is willingness is also depends on various factors. For example, many household they might concern it will cause battery degradation and might also cause some maybe ranging anxiety for their next trips. So this will also need to be considered as part of like rewards. So I would say maybe the next step we might replace the fixed rate, but based on the like timely uh, like the demand from the grid, and also consider the battery degradation issues associated with this. Yeah, but it's
Yeah,
a
and
very good point. Yeah.
yeah, and I see Kara's provided a few papers from your group on this, and
Oh, thank
just
you, Dr.
showing the size of this research community from her former student Matt Dean, who's now an assistant professor at UCI, and his student is the last speaker in this session. Um, Janak had another question, just because we do have the time for it. Can you say a word on the business, if the business case exists for this, considering this can be beneficial to operators?
Currently, I would say, from our results, I would say the V2G capable infrastructure is really expensive, so it requires very high upfront cost. Um, so this will be kind of like a limitation for the V2G like to be employed currently, but hopefully like uh, the charging technology and also the infrastructure can be more mature and the prices can be declined. And then that will be much better like for the fleet, like for the operators, they can have like more for example, more revenue through the V2G and also help to reduce the emissions through this technology. But from the near term, I would say it's very costly for this upfront infrastructure deployment. Yeah.
Great. I don't see any other questions in the chat box. I had sort of a couple of questions that I think relate back to some of the questions that have already been asked. So my first question is V2G has it been implemented anywhere?
Uh, As I think I saw some case study, like maybe in the
Yeah.
California, they have pilot some like some tasks for the V2G, but they didn't deploy at scale. I would say,
Yeah.
yeah.
Okay. Yeah. And then another question that I think you responded to this was more of a battery question than a transportation
Mhm.
engineering question. So with V2G, it seems like there would be some concerns about additional charge discharge cycles with that, right? So
Yes.
increased battery degradation. So that's something that you're sort of thinking about, but hasn't been incorporated into the model yet, right?
Uh, yes. So that's also like one cost component we considered in our
Mm.
objective function because the V2G can bring both environmental benefits and also revenue for the for the operator or for the household, but they will also have certain negative like costs. We also need to like incorporate this. So yeah, like in our designed optimization framework, we consider both revenue and cost associated with V2G.
Great. Um, oh, we have one more question. Just we do have the time for it. So, has the extra cost of degradation on transformers for the distribution system, I guess,
Oh,
been incorporated? Yeah, be
yeah, I
considered.
mean, that's a very good point. So, currently we didn't like incorporate the degradation cost for the like transformers, but just on the vehicle side. Yeah, but I
Mhm.
think like maybe for the next step, it's also like very good point to incorporate. Yeah. Thanks
Yeah,
for
and it's definitely a good reminder of how much transportation and electrical engineering is becoming integrated. I have a master's student whose undergrad is in electrical, so yeah. So, okay, so our next speaker, I believe it will be Janak Parmar speaking. Will be understanding perceived usefulness of battery swapping technology among EV users. And so this is work from the University of Birmingham. Yeah, so whenever you're ready, if you want to share your screen.
Just in a minute, I'm sharing my screen.
Yeah.
Please say if it is visible to you.
Yeah, I see it.
Okay, the full screen, right?
Yep.
Okay. Yeah, so this is one of the short research we have done in last year. I'm presenting today, which is about the paper actually asked the user side question about battery swapping, not whether it works technically, but whether the people who would actually use it think it's useful. So the evidence is UK EV drivers database analyzed with structural equation modeling. So we all know that EV uptake is accelerating, but the setup is a tension. If we see UK EV adoption is strong and strengthening, roughly a quarter of the new car sales in 2025, and 70% of the drivers say they will buy an EV within 5 years. The network is growing too. I mean, public charge points up 26% year on year, but the friction, I mean, hasn't moved. So charging time, limited range, and uncertain availability are still the things drivers name most often, and not the last figure. I mean, that's from our own sample. Only 13% of the people who already own the EV are fully satisfied with public charging. See the bar comparison as well. A typical, I mean, fast charging session in the policy discussion is 30 to 60 minutes. Battery exchange reported in the literature is 3 to 5 minutes. So there are two structurally different responses to these. Either charge faster, which shortens the vehicle, vehicle, uh, the driver and the grid connection are tied to the same moment, or don't charge at all. We can swap the pack and decouple when energy is drawn from the grid. This paper is about second. So swapping is a state policy in Asia, but a pilot in Europe still. So two very different trajectories. China treats swapping as infrastructure, a 3-year action plan already in place targeting 28 million charging and swapping facilities, over 20,000 swap stations already subsidized. And one of the organization, NIO, running battery leasing as a mainstream consumer product. But in Europe, it is currently they treats is like a pilot. Power swap, for example, in Sweden, around 30 NIO stations across 5 countries. Then Stellantis and Ample in Madrid. Then nothing is deployed currently in UK. So the user evidence base is almost entirely the Asian, and that's the gap this paper actually sits on. Now the bottom band, if you can see, the BYD went from 1 megawatt to 1.5 in 12 months, around 400 kilometer of range added in 5 minutes, with roughly 5,000 units already installed in China and 3,000 announced in Europe. And crucially, those stations buffer through on-site storage, which contains, not just swapping's time advantage, but its grid decoupling argument too. So if the energy case is converging, what decides it is what users actually value. There's an empirical question, and it's the one we actually answer. So we already know that perceived usefulness is, central determinant to technology acceptance. Swapping is routinely framed as a fix for range, anxiety, and charging delay, and deployment is concentrated in Asia actually. The gap is on the left actually. If you see, acceptance evidence seats in Asian markets. Kegel and colleagues, from 2025 is the nearest European study, and that's in Germany. There is no published UK user evidence. So we asked two questions here. Which beliefs shape perceived usefulness among UK EV users, and which user characteristics differentiates who finds it useful? On the right is the framework. So the term gives us the dependent construct, not the independent in particularly our case, but terms generic and antecedents, if we see, don't travel well to the technology whose usefulness actually depends on infrastructure that doesn't yet exist. So we extend it with four context-specific constructs: the adoption potential, then energy system constraints, then battery compatibility concerns, and the perceived operational barriers. So these are the four extended constructs derived by EFA in our study and confirmed with CFA again. So these are extension of term, not replacements, I can say, not the expected sign besides each box. Positive for adoption potential, negative for two other barriers constructs, and 3 of 4 behave as predicted. Actually, one does not, and I will come back to it later during analysis. So briefly, web survey in Qualtrics with 3 sections: travel and vehicle profile, then current charging behavior, then attitudes to alternative charging, with 14 attitudinal items on the 5-point Likert scale. Expert review, then piloted before launch. Recruited through Prolific, screened for verified current UK EV owners, April to May 2025. That was the survey period. 795 accessed, and the 728 valid responses after cleaning. The map shows the coverage across all UK regions, with the largest share is about South East, and then Scotland and the London. On analysis, EFA, then CFA to establish and confirm the measurement structure, and then covariance-based SEM, structural equation model. One point worth being precise about: perceived usefulness is a latent construct with 4 ordinal indicators. The estimated and we estimated using WLS-MV on polychoric correlations, which is the appropriate treatment for the ordinal data. So who answered our questions? So concentrated in the working age band with 53% between 35 to 54 age group. The dominant purchase motivation is the economic cost savings at 80%, ahead of environmental concern, which sits at 60%. And these are heavy users, I can say, because 64% of the drivers actually drive 5+ days a week, and 79% commute in the vehicle. The 4 figures below matters the most for interpretation, because around 82% hold a degree or higher, so they are well educated, we can say. Then 78% have household income above 40K. Then 84% have dedicated parking at their home place, I can say. And the sample is roughly balanced on gender, with 51% females, which is notable since earlier EV adoption studies skew heavily towards males. The interpretation line is the one to say aloud, because this is not a casual EV interest group. These are frequent users with stable private charging and relatively high socioeconomic status. Also, please note that non-adopters, flat dwellers without off-street parking, and lower income drivers are underrepresented over here, and their view may differ substantially. So these slides sets the use case. Home dominates with 85%, public at 41%, workplace at 23.5%, and home charging is slow and unhurried. We all know that 72% of home sessions run over 3 hours, and which is fine when the car is generally parked overnight. Public charging behaves completely differently. Half of public sessions are under an hour, and the and the reasons people pick a particular station are speed of charging at 73% and proximity at 64%, well ahead of cost. Satisfaction is the striking part. Actually, if we see only 13% of the participants were fully satisfied, and 31% dissatisfied outright. I mean, for public charging availability. So the picture is a two-speed system, we can say, private convenience and public friction. That's precisely the gap a rapid alternative could occupy, particularly when public charging is slow, crowded, or unavailable. So this is the I mean, say the how the attitudinal items were rated. I am showing a 9 only here because of the readability. Three things. So first, look at the top bar. I mean, the strongest agreement in the entire study is 82% about a barrier. That a universal system is hard to build given differing chemistries and pack sizes. Not a benefit. It's a barrier. So it's notable. Second, utility is recognized broadly. Nearly 79% see value where CT charging is insufficient. Then 71% expect swapping to play a crucial future role, and 68% think it reduces the range anxiety as well. Then third point, this is the one I mean, most want you to remember, because only 45% of the respondents would actually prefer a swap-capable vehicle. It's the lowest item on the chart. Maybe they think they already own the EV and don't want to spend another bunch of money just for I mean, capable EV which can swap the batteries. And 59% are satisfied with how they charge today. So recognized usefulness is not expressed demand. Those are different things, and conflicting them is how you end up with infrastructure nobody actually uses at the end. So this is the results of confirmatory analysis, factor analysis. And just for reference, firstly, EFA established the factor structure, then CFA tested and confirmed it, and 5 constructs across 14 indicators. These are the standardized loadings which are presented over here within the range with alpha and composite reliability and average variance extracted. The structural model was estimated afterwards on the confirmed measurement model. So this is the full model. This is a part of a big study which we are just following up right now. So I'm just presenting a full model which we have right now. So 4 attitudinal latent constructs on the left with 4 observed and significant covariates on the right. Perceived usefulness in the center, which is the dependent variable in our case. So the left side first, positive adoption potential is by far the strongest association with 0.838 beta, and then energy system constraint with positive as well at 0.295, and battery compatibility concerns, the red arrow, I mean the third one, strongly negative at minus 0.580. The largest break in the model, because this is the most negative part in this model, and perceived operational barriers at plus 6.638. That is positive, where we expected negative actually. Hold on that thought. I will come back to it later as well. On the right, there are socio-demographic characteristics, gender at 0.49409 positive. Then EV range negative at minus 0.147, purpose of use for commute versus non-commute at again positive at 0.358, and satisfaction with public charging weekly negative at minus 0.86. So fit is acceptable again. If we see with the indices shown here, one point to mention that these are the associations, not the causal effects. The data are cross-sectional. So the key findings, pulling things together. The top table is the attitudinal story. So belief in the benefit dominates with highly positive PAP, positive adoption potential. And then awareness of grid limits goes with higher usefulness, not lower. Then interoperability, doubt is the strongest barrier in the model as we see in the model, and then operational barriers at plus 0.638, the informative surprise, because conceptually you would expect that people who foresee practical problems to rate swapping as less useful, but we find it positive, and the reading we favor is about problem recognition. Users who perceive shortfalls in current system see swapping as the remedy for them. Okay, so the needs to be recognized and addressed for greater adoption. That's consistent with, again, the study I already mentioned, Kegel and colleagues. They found that BEV interested drivers treat swapping as a problem solver. So our ongoing further analysis will test whether that holds across all users or concentrates in particular segments. Sorry. But there is another about how the okay, I mentioned this. Oh yeah. And now the thing is, who finds it useful? So women report higher perceived usefulness, consistent with the evidence from our survey that they report greater concern about charging availability and personal safety at public sites. Then longer range EV owners report less usefulness because more range, less perceived need for the battery swapping. Then for commuting case, because they report more positive usefulness because obligations put a premium on turnaround time. They don't want to wait for the charging, we can say. And of course, the lower satisfaction with public charging goes with higher perceived usefulness. Yeah, so this the discussion. Now we discuss about the policy priorities. So the first one is about standardization. So the standardization is a precondition, not a later refinement that we can say. And because compatibility concern is the single largest break in the model, and 82% of the sample recognizes the problem. So common PEC interfaces, a certification of swap-ready vehicles, and open connector specifications are the enabling conditions on which everything else depends actually. And then the second one, deploy where the system constrains users. So perceived usefulness rises with recognized barriers. So that points to dense urban areas without off-street parking and corridors where public provision is thinnest. So swapping as a complement that fills the gaps, charging lives, not a replacement for it. Then the third one is about fleets, and high utilization vehicles are the viable entry point. We see value is higher when uptime is monetized and range is short. So depot-based swapping for taxi, private hire, and last mile delivery converts the strongest perceptions into a most measurable operational returns. So this is little bit of extended thought, I would say. And the fourth is about close the gap between recognized utility and personal choice. As I already mentioned earlier, that 71% expect a crucial future role, but 45% would choose one. That distance is where the policy work actually is. And it's about battery health guarantee, ownership terms, and demonstration exposure, not just about awareness campaigns. So actually demonstrating what is happening on the field will be much better compared to just making them aware about how the things are through the campaigns. The conclusion. So what this means for battery swapping in the UK particularly. So first and second together, UK EV users frame swapping as a system fix, not a personal preference, and they judge it as an infrastructure rather than as a product. So what drives perceived usefulness is beliefs about what the technology resolves at the system level, and the tech attitudinal constructs outweigh every demographic predictor in the model, as we see in the previous slide. Then third is about interoperability. That is the binding constraint. Because it's the strongest negative association in our model, and simultaneously the item drawing the highest agreement in the study. So that makes standardization the policy lever with the widest reach and the clearest empirical warrant. Then fourth and fifth taken together, the receptive segment is identifiable and reachable. The constraint up time dependent short range users, which makes targeted early deployment a testable strategy rather than a mass market gamble. So as megawatt charging closes the speed gap, we see the case for swapping rests less on refueling time and more on specific constraint that the users actually report or they face on field. So the closing line can be like battery swapping. So UK prospects rest less on low how quickly it can refuel a vehicle rather than on whether the ecosystem can be made to work as one. And that is the policy choice, not a technical limit. So the last slide about how this research actually can be extended and what we are right now doing. So on the left is work in progress actually, and each line has its own policy payoff. So latent class analysis tells us whether distinct user segments interpret usefulness differently, which moves policy from average effects to the targeted design. Then IRT tells us where along the continuum acceptance actually shifts, and Bayesian SEM gives us the parameter uncertainty that appraisal work needs. And on the right, where the evidence base goes next, because there is always a limitation of user participation in the surveys. So beyond current owners, to the non-adopters, then drivers without off-street parking and fleet operators that swapping would most plausibly serve, from stated perception to observed behavior through the stated choice experiments and pilot evaluation, and the integration with citing grid capacity and cost modeling so that acceptance evidence can feed an actual investment case. And that's where we are working and plan to work. Yeah, so thank you, and now I'm open to questions.
Thanks. Any questions for Janak? Yeah. Okay, so Jane Gould asks, is there a case to be made from Asia, perhaps, that the cost of owning and operating a battery swapping vehicle is significantly favorable to the driver vis-a-vis Western models of leasing or ownership?
I'm just reading the question again. Okay.
Yeah,
Sorry
yeah.
that I couldn't hear properly.
Yeah.
So it's a case to be made from Asia, perhaps, that the cost of owning and operating a battery swap vehicle is significantly favorable. Oh yeah, this is a great comparison, I can say, because as I said already, I mean, in Asia, particularly if we think about China, so the things are very much established there. And uh, compared to the Europeans and including UK, as I already said, there is nothing happened in UK in terms of battery as a service bus system or battery swapping system, we can say. So this is a really good case to, I mean, consider the cost of owning and operating a battery swap vehicle is and the Jane mentioned, because this is significantly favorable to the driver, as he said. Yeah.
Yeah, any other questions?
I hope I actually
Yeah, I think
understand the
this is your
question.
co-author. We're working on this comparison with China through a stated preference experiment at
Yeah.
University of Birmingham. So good. So it sounds like you're working on that. Any other questions? Not a question, but just a comment as a EV owner that I agree kind of the universal system is sort of one of my great frustrations, especially with public charging systems, that you don't know what kind of plug won't necessarily be there. Sometimes you don't know if it's going to be charging you. Well, you can look up, right? But the systems vary by if it's charging you per kilowatt hour or by minute, or so it's much less uniform than in the gasoline gas station system. So I think that uniformity should hopefully come. But any other questions? Okay, well, thank you again, Janak, for the presentation. If there's other questions, feel free to put them in the chat box.
Thank you.
Otherwise, our last speaker will be Amin Akbari from University of California, Irvine, who I remember when he started as a master's student, and I now see that he's doing his PhD. So good to see how everyone progresses.
Yeah. Hi, Jason. Good to see you as well.
Hi. Yeah.
Um,
Whenever you're ready.
sure. Just let me share my screen. Right. I don't when I'm in the full screen, I don't have access to the Zoom, so just let me know if you can see my full screen.
Yeah, I can see it.
Awesome. All right. So let's get started. Hi everyone. Thanks for having me. And so my name is Amin Akbari. I'm a PhD candidate at UC Irvine at the Institute of Transportation Studies. This is a joint work with my advisor, Professor Matthew Dean. So today I want to talk about the electric vehicle charging and airport parking facilities. We looked at one real airport and we used their own data, their charging session, their electricity bill, and the cars that actually show up there. So let's get into it. So before we talk about charging, I want to say something about the parking in the airports in general. So airports makes money in two ways. There is aeronautical revenue, which is the landing fees, terminal fees, and aviation side. And then there is everything else, which is about 40% of the total. And inside that everything else, parking is the biggest piece. It was number 2 back in 2019 behind the retail. By 2023, it moved into the first place at 24% based on the airport economic report. So parking is not a side business for an airport. It's one of their largest revenue sources. So the research on managed charging also has focused on, homes, workplaces, and depots or public charging. So places, where people plug in overnight on a predictable schedule and where, household time of use rates makes it makes it worth doing. The reported values ranges, widely from net losses to few $1,000s a vehicle per year, depending mostly on the price signal and, plug-in patterns. So, airports barely appear in the literature, and when they do, the arrival time and the prices are usually assumed rather than observed. So, and also there was a study from ACRP published last year that looked specifically at the charging in the US airport parking facilities, and they found that 93 out of 145 hub airports offer public charging today. 10 years ago, that was only 37. So even every large hub in the US has it now, basically, and it's mostly level 2. So, but 25 the airport that they surveyed, only 2 of them do any kind of load management, and 20 of them, they don't charge anything for electricity. So the infrastructure is going faster than anyone is, learning how to operate it. So why airport specifically? Airport parking is different from every other place people charge. You park at the mall for 2 hours, you park at home overnight, but in an airport you park for days. And, for example, on the right-hand side is what it look like in the San Jose International Airport data. We found that the average car is plugged in for 24 hours and it's only actually charges for about 4 of them. So that's not a problem, actually. That could be opportunity, because during those 20 hours, you can decide when the energy flows. You can even decide, which direction it flows. And, the driver never notices because they still, come back at a full battery. But today, nobody does this. The charger is just ran flat on the moment you plug in and then sits idle. So no awareness of prices, nothing captured from that park battery. So the question we are asking is pretty simple. How much is that idle time actually worth? And what has to be true for it to be worth anything? So there are two ways to use the idle time, as you probably already know both. The first is smart charging or vehicle one grid. The car, it still only charges every energy only flows in a one way, but instead of charging the second you plug in, the optimizer picks the cheap hours, for example, same energy delivered, same full battery at the end, and just basically bought it at a better time. And the second one, the right-hand side, is vehicle to grid. Now energy can go both directions. Buy when it's cheap and sell it back when it's expensive, and refill before the driver returns. So the battery basically becomes kind of temporary storage for the facility. Oops. All right, so here's how we set this up. Basically, we have three inputs on the left-hand side, the airport's, own charging session, which gives us, when car arrive, how long they stay, how much energy they need, the electricity prices from the tariff the facility is actually built under, and the real mix of the electric vehicles registered in the county. So those basically then fit into a simulator that run a full year, moving, 15 minutes time steps. It generates arrival, samples what car show up, and assigns to the port. So then at each step, an optimizer decides what every connected car should do, charge, wait, discharge in the vehicle to grid cases. So it only executes at one time step, and clock moves forward, and car come and go, and it starts again. So that's kind of a model predictive control approach. The important part is that it never sees the future. It plans with what an operator would actually know at the moment. And out of that, comes the kind of basically the results, the charging schedule, basically, the aggregated results like energy cost, discharging revenue, peak demand, and net profit, or etc. So the first input, the charging data. So this is the every charging session in our case study airport for all of 2024. More than 3,700 charging sessions observed in full year across 15 level 2 ports. On average, the 21 kilowatt hour energy delivered per session. And the heat map you should see on this slide basically kind of shows the mean arrival rate based on the hour and day of the week. So you can see immediately everything happened basically between 4 and 7 in the morning. That's the early departure bank. So every arrival in our simulation is drawn from this kind of logic, and the right day, the right hour, matching what the airport actually sees. Second input, the prices. This is the actual rate the plan, the parking facilities on, the Pacific Gas and Electric, the utility company, the airport uses, the same commercial tariff called P-20P, with hourly pricing actually layered on top. So two things matters here. First, the prices are published a day ahead, so the controller kind of knows the tomorrow's prices in the horizon. And second, the spread between the overnight low and the evening peak in our data. So you're looking at roughly 24 cents a kilowatt hour. And that's really important here because everything you're doing here is arbitrage charging. It depends on the price spread. And also you can see on the right-hand side, we included, the time of use structure for the same plan. So the fact about it, these rates are kind of low compared to the residential, or public charging. It kind of makes sense because most of their bill comes from the demand charges actually. And the third input, the car themselves. So a lot of studies assume, one representative vehicle or maybe 3 or 4. We didn't want to do that because, battery size drives everything here, how much energy car needs, how much it can give it back. So we use the actual registration for this county that the airport actually based on. The assumption behind that was we assume that most of the people are going to use the airport parking are from this same county, right? The Santa Clara County. So, and as you can see here, for example, the Tesla is dominated, almost 70% of our sample distribution, which kind of makes sense, for the US and especially in the California, and which they have around a 70 kilowatt hour battery size on average. So the simulator, right? So every 50 minutes, as I said, the car arrives. Each one gets a battery, a state of charge, and departure time. And then the first real decision after that, which port does the car go, right? And here's the thing about the airport that most people are parked for a day or two. And if you are there for 20 hours, level 1 probably would be completely fine for you. So a slow charger has all the time in the world. And so the rule is we use a kind of simple heuristic approach to default is to level 1. Before assigning, we check whether the level 1 is alone can get the car to the target in the first in the time that it has, and if it was okay, it goes to the level 1. If not, because it's a short stay or the battery is nearly empty or something like that, then it takes the level 2 port that keeps the fast charges free, for the car that actually needs them. And one more thing before the optimizer, this is like before the optimizer sees anything, so we keep we cap each car's target at whether they can physically deliver, so the optimizer never handed a promise it can keep. Next on the optimizer, so what we built is a model predictive control, as I said, and underneath is the mixed integer linear programming. Every 15 minutes, it resolves over all the cars currently plugged in. And the objective for us has like 4 components. Is maximizing the profit sold back to the the energy sold back to the grid, which is the revenue. Energy bought from the grid, that's the cost. Battery degradation, price per kilowatt hour. Discharge for vehicle to grid cases, and the demand charges on the highest moment of the week. A few key assumptions here: that prices are published a day ahead, so the controller knows them. Departure times are stated at the check-in, and we don't forecast the future arrival at all. And the main constraints are every car lives at the 90%. This is our assumption, and nothing goes below the 10% kind of reserve floor in the vehicle to grid scenarios, and it can charge and discharge at the same time. And level 1 chargers, cars can only do the normal charging, so there is no managed charging can be executed on them. Okay, so let's look at the results. So this is a full year across all 3 cases: normal charging, smart charging, and vehicle to grid. So first thing, the service is identical in terms of the same amount of vehicles are observed and same energy delivered. So everyone lives at the same state of the charge. So nothing that follows comes from the charging less or turning people away. Smart charging in these kind of naive results costs electricity costs by about 60%, same energy, just about at a better hour basically, and vehicle to grid kind of flips it. The facility stops, being the cost and starts making money. So, but this kind of baseline scenario, it has no battery degradation, no demand charge, perfect efficiency, and you sell and back at exactly what you paid for. So none of them is kind of true in the real world, obviously. So treat this is kind of upper ceiling or upper bound, not a forecast. So now let's change one of those assumptions in the baseline one at a time and see what happens. So for example, battery degradation is the one that hurts the most. The whole idea of the vehicle to grid is that you cycle in someone's battery and the battery wears out. So once you start, charging even a small amount of that wear, a lot of that trait stop being the worst doing, pushing to the high end of what the literature kind of suggests, and the optimizer basically, stops discharging altogether. And the sale price, for example, is more straightforward. If the utility pays you less for what you send back, you send back less, and it scales pretty much 1 by 1. Efficiency is where the 2 strategies kind of split. Every time energy flows in or out, you lost a little. For smart charging, that's kind of just overhead. You just still owe a driver a full battery, but so you buy more to cover the loss, right? So for the vehicle to grid, it's kind of opposite. You pay the loss twice, once in and once out. So some trade stop clearing, and it just does fewer fewer of them. But let's look at the demand charges actually, right? So looking at the left side, where there is no demand charges at all, smart charging peaks 37 higher than just plugging and letting doing the normal charging. Vehicle to grid also would be like 83% higher. So the managed charging strategies here are actually worse for the grid than doing nothing. And that makes sense, when you think about it. Why? Because if you tell an optimizer to find the cheapest hours, every car goes to the same cheapest hours and everyone pulls in at the once. So now by adding a small amount of the demand charges, by the way, smart charging peak drops 60% below the unmanaged charging, and suddenly it would be kind of the best option for the grid instead of the worst. And that actually then it flattens out, and going higher going to the higher amount, it barely moves anything. So almost, the entire response is, basically bought at the very low end. All right, so next set of the result, same 5 parameters here, but now we are looking at what the facility actually earns week by week across the year. The demand charge is the only one that, wipes out the value, at the rate that actually applies to the site. This size, about 2/3 of the profit is almost gone. Battery degradation eats into it like faster than anything else, but it never kind of quite kills it. So even at the top of the range we tested, a typical week is still kind of could make money. And efficiency barely matters. We pushed it well past what real hardware does, and it only costs about 15%. But the thing I would really ask you to look into is how tall, kind of wide these boxes are. The week to week variation is huge. Some weeks lost money even in the best case. So this isn't like a steady daily arbitrage. Most of the value comes from the small number of the weeks where the price spread happens to be unusually wide. So that's also should be mentioned. But so far everything that I showed you was assumed on the 15 level 2 ports, right? Now let's change the charger types themselves, right? So level 1 is the much better for the grid. And all level 1 caps the site at about 16 kilowatt instead of 83, so we don't have the peak demand problem anymore. That's an 80% cut, and you get it without any controller at all. But level 1 can discharge and neither do a smart charging. So the whole revenue side disappears. Now, in terms of the service question, but everyone is still gets support in all 3 cases because we have the same number of the vehicle that's served, but it still kind of depends on how many ports that they are and how fast they are. What charges is how full people leave. So on the mixed scenarios, in 94% it still hit the departure state of the charge target. On level 1, charges, it drops 77%, so nobody gets turned away. Some people just leave with a less sharp. And the mix is kind of sweet spot we found. For example, in our scenario, it would be like 8 level 2 or 7 level 1. Peak drops by 40%. It's still profitable. That works because of the rule from earlier. Level 1 only gets the car it can actually finish. One thing we're saying here is that we are not optimizing which car goes to which charger. It's a simple rule basically we applied when the car arrives. We think that if you did optimize that assignment and put it in your optimization, these numbers probably would get better. And the last slide. So 4 things take away from this kind of research. If first, the smart charging is the easy win for the airport. 60% of the electricity bills, no new equipment, and it's held up under every single scenario that we tested, and almost nobody is doing it. Based on that report, only 2 airports out of 24 airports only doing that right now. And second, vehicle to grid does work, but it's fragile, it's not reliable. If we change those parameters a little bit, all of those kind of profit would be taken away, and it will be gone. And third, that kind of surprised me, the cheapest is not the same as the best for the grid. Without demand charge and managed charging makes the peak worse actually. So a small demand charge can actually fix it. And the fourth one, the charger mix could be the real design choice for the airports. Splitting the level 1 and level 2 cuts the peak by 40%, and it still makes money. So for the airport today, I would say do the smart charging, and for utilities, the tariff is what decide whether any of the rest of these worth doing. And yeah, thank you so much for listening, and happy to have any more questions that you guys have.
Yeah, great. Great. I mean, very, very interesting, I think, in this session to see sort of the diversity of applications on this topic. Are there any questions I mean, I can see in the chat we've had a bit of a discussion on parking costs, and
Right.
Jane Gould mentions that at Logan Airport in Boston, they offer free charging for
Yeah.
ride-hail drivers in a nearby off-site location. Any questions though?
Yeah, that's true. Unfortunately, most of the airports in the US they offer free charging. They still charge for the parking though, but I mean that's actually could be the problem because you kind of put the ceiling of the people's utility at high, and later on, if you want to change that, if you want to like execute some these kind of programs, you would probably also have to expect how you change the people's utility. So because these research I just showed you with that assumption that we do not consider the people's acceptance at all. We assume that everyone's gonna opt in and agrees with the terms and conditions basically.
Great. Okay, well, I guess if there aren't any specific questions for Amin, maybe maybe what I would suggest is we've had several really good speakers this session, and we have a few minutes left.